Picture this. A patient is fitted with a remote, continuous AI heart monitor.
Right, like one of those really advanced wearables.
Exactly. It is this absolute marvel of modern medicine, right? Designed to track his vitals and use artificial intelligence to detect, the slightest anomalies in his cardiac rhythm.
Sounds pretty standard for cutting-edge healthcare right now.
Yeah, but here's where it gets weird. So one evening, he's just sitting on his couch watching the news, and his cat, whose name is Shirley, jumps up and sits squarely on his chest for like an hour.
As cats tend to do.
Right. And Shirley, like a lot of pets, has a standard tracking microchip implanted under her skin by the vet.
Oh, I see where this is going.
Yeah, so the patient is absolutely stunned the next day when he receives this automated, highly detailed health report from his state-of-the-art medical device. And the entire report is formally addressed to Shirley.
That is, it perfectly illustrates the current paradox of this technology.
It really does, right?
Yeah, because it is simultaneously the most advanced analytical tool humanity has ever created, and yet it completely lacks basic common sense.
Just zero context.
Exactly. It saw a chip, it read a name, and it just processed the task it was assigned without the human context to realize, hey, I'm monitoring a feline right now.
Which raises the ultimate question for us today. If artificial intelligence is supposedly smart enough to assist in complex robotic surgery, how in the world can it also be so easily confused by a house cat?
That's a great question.
So welcome to this deep dive, everyone. I want to give a special welcome to the students of the Dr. Sam Pack College of Business at Tarleton State University, as well as, all the working professionals tuning in to Managing the Future, the MIS podcast.
Glad to have you all here.
Today, we are taking a really extensive look at Module 21, Artificial Intelligence, and this is all based on the insights from ConnectMaster Management Information Systems by Richard Tedmon and Casey Wilhelm, the 2026 release.
It's a massive topic.
It is, but before we get completely lost in the matrix of neural networks, we need to do a quick reset on the foundation we built in the last module.
Yeah, that foundation is absolutely crucial. So in Module 20, we focused on computer software and buying a computer.
Right.
We established that fundamental split between hardware, which is the physical machine itself, and software, which, provides the instructions.
The brains versus the brawn, essentially.
Exactly. And we looked at system software, specifically operating systems like Windows or Linux, which serve as the interface between you and that hardware. And then we looked at application software, which are the actual programs we use to execute tasks.
And we spent considerable time evaluating hardware limitations, too. Like, we talked about how the processor acts as the brain, but RAM acts as the short-term memory.
Right, the workspace.
Yeah, and the more multitasking you do, the more RAM you need to prevent the system from bottlenecking.
Which is actually the perfect bridge to today.
Right.
Because if Module 20 was about building the engine of the computer, well, Module 21 is about making that engine drive itself.
I love that analogy.
It fits, right? Because artificial intelligence requires astronomical amounts of data, storage, and processing power. It pushes the exact hardware specs we evaluated last time to their absolute limits.
Just to move a computer from simply executing basic, pre-programmed commands to actually learning and predicting on its own.
Exactly.
Well, before we jump into how it actually learns, a quick reminder for everyone listening. Please take a second to like, subscribe, follow, and share this deep dive.
It really helps us out.
It does, and definitely leave a comment below. It is the absolute best way to stay updated with the course material, and it genuinely helps us keep these deep dives coming. Just think of it as joining your classmates for a virtual study session.
We always look forward to seeing how you apply these concepts in the comments, so definitely chime in.
All right, let's start with a baseline definition. Because, the media tends to portray AI as this sentient robot plotting to take over the world. But from a business perspective, it is much more grounded than that, isn't it?
Far more grounded. Tedmon and Wilhelm define artificial intelligence as the study and application of processes that combine computer science and data science to enable automated or computer-assisted problem solving.
Okay, so less Terminator, more supercalculator.
Exactly. At its core, it is an incredibly advanced statistics engine. It uses complex algorithms to identify patterns in data, and then it uses those patterns to make classifications or predictions.
But the timeline in the textbook reveals something really surprising. We talk about AI like it's this brand new phenomenon that just dropped out of the sky in the 2020s.
Right.
But the foundational concepts have been around for nearly a century.
We actually have to trace it all the way back to 1950. That's when the legendary mathematician Alan Turing published a paper called Computing Machinery and Intelligence.
Oh, right, where he introduced the Turing test,
Exactly, what we now call the Turing test.
the imitation game.
Yeah.
But, like, functionally, what did that test actually measure?
So, Turing proposed a theoretical benchmark for machine intelligence. Imagine a human evaluator having a natural language, text-based conversation with two entities hidden behind a wall.
Okay, kind of like a blind chat room.
Right. One is a human, the other is a machine. If the machine can converse so convincingly that the evaluator cannot reliably tell which is the machine and which is the human, well, the machine is said to have passed the test.
So it wasn't about whether the machine was actually conscious?
Not at all. It was about whether it could successfully simulate human thought processes to an indistinguishable degree.
It basically set the goalpost for the entire industry. And then, just a few years later in 1956, American computer scientist John McCarthy officially coined the term artificial intelligence at a conference at Dartmouth College.
And that essentially kicked off the formational years of the industry. From roughly 1958 to 1966, we saw the first real attempts to build these systems.
Right. McCarthy himself developed LISP, which became the foundational programming language for AI research.
Yeah, and this era also gave us ELIZA in 1966, developed by Joseph Weissenbaum. ELIZA is widely considered the very first chatterbot.
I actually find ELIZA fascinating because it was designed to simulate a Rogerian psychotherapist. But it wasn't actually thinking, was it? I mean, how did it pull off the illusion of conversation on 1960s hardware?
It used a very clever but very rigid keyword flipping mechanism. It was early natural language processing.
How did that work in practice?
So if a user typed, "I'm feeling very sad today," ELIZA's programming would scan that sentence, latch onto the keyword sad, and use a predefined script to flip it into a question.
Oh, like, why do you think you were sad?
Exactly. It gave the illusion of empathy and understanding, but under the hood, it was just executing simple pattern matching.
Which is an incredible parlor trick for 1966.
It really was.
But if we followed the timeline in the text, that early optimism hits a massive brick wall. There is a period from 1987 to 1993 known in the industry as the AI winter.
Yeah, a really bleak period for researchers.
What actually caused the freeze?
Funding completely dried up. Both public governments and private corporations just stopped writing checks for AI research.
I look at this and I instantly think of the dot-com bubble bursting in the early 2000s. You know, people get so hyped about a new technology that the expectations completely outpace what the physical infrastructure can actually deliver.
That is the exact mechanism of the AI winter. In the 1980s, governments and corporations poured billions into what they called expert systems.
Right.
The Japanese government famously spent $850 million on the fifth-generation computer project, promising machines that could converse and reason.
Which didn't happen.
No, it didn't. There were managerial advisory systems like Alacrity, which boasted having 3,000 predefined rules to help executives make business decisions.
But wait, 3,000 rules isn't intelligence? That is just a massive labyrinth of if-then statements. Like, if the competitor lowers their price, then we lower ours.
And that was the fatal flaw. They were trying to manually program every possible scenario a machine might encounter, which is impossible.
Right. The real world is too messy.
Exactly. These expert systems were incredibly expensive to build, a total nightmare to maintain. And the computing hardware of the late 80s simply lacked the processing power to execute them quickly.
So they just abandoned them.
Yeah, investors looked at the dismal return on investment, realized that technology couldn't match the promises, and pulled their money out.
You know, if you're a student or a manager listening to this right now, this historical tangent is deeply relevant to your career.
Absolutely.
Understanding that AI is iterative software and not magic prevents you from falling into the exact same trap today. If you are an executive evaluating a multi-million-dollar AI integration for your company, you have to look past the buzzwords.
You really do.
You have to ensure the investment has a clear, measurable ROI and that your company's current hardware and data infrastructure can actually support it. Otherwise, you're just buying an expensive parlor trick.
The underlying lesson of the AI winter is that technology must solve a real business problem efficiently, or it will be abandoned. Fortunately, though, the hardware eventually caught up.
Yeah, the textbook marks 1997 to 2011 as the era of resurgence.
And this is where we start seeing massive public milestones. Like in 1997, IBM's supercomputer Deep Blue defeated the world chess champion, Garry Kasparov.
But how did it do it? Because it wasn't just relying on if-then statements anymore, right?
No, Deep Blue utilized massive parallel processing. It was capable of evaluating 200 million chess positions per second.
Wow. 200 million?
Per second. It didn't understand chess the way Kasparov did, but it had the sheer computational brute force to map out the mathematical probability of success for millions of potential moves in an instant.
That is just raw power.
Yeah, and then the evolution accelerated. By 2003, NASA's Spirit and Opportunity rovers were navigating the rugged surface of Mars autonomously, making pathfinding decisions without waiting for human input from Earth.
And then came the moment that really brought AI back into the public consciousness, 2011, when IBM's Watson went on the game show Jeopardy and just dominated Ken Jennings, the greatest player in history.
That was a huge moment.
I remember watching that. Jeopardy clues are full of terrible puns, nuanced wordplay, and, cultural context. How did a computer parse that?
So Watson represented a massive leap in natural language processing. Instead of just searching a database for keywords like ELIZA did, Watson was programmed to generate thousands of hypotheses simultaneously.
Oh, wow.
Yeah, it would break down the complex sentence structure of a clue, analyze the contextual relationships between the words, cross-reference that against a massive, localized database of encyclopedias and literature, rank the probability of each potential answer, and then hit the buzzer all in less than 3 seconds.
That is insane. It proved that machines could handle the messy, unstructured nature of human language.
And that same year, Apple released Siri, putting that exact kind of linguistic processing power into the pockets of millions of consumers.
Which basically catapults us into the modern era, right? From 2012 to the present, where the growth curve just goes completely vertical. We start seeing systems that invent their own processes.
The breakthroughs become highly complex. Google developed a neural network that learned to identify cats in YouTube videos without ever being explicitly programmed to know what a cat looked like.
Wait, it just figured it out?
Yeah, it just watched millions of videos and recognized the visual pattern on its own.
That's wild. And then in 2017, Facebook had those two chatbots that were tasked with negotiating with each other in English to trade virtual items.
I love this example.
I remember reading about this. The programmers left them alone, and the bots realized that English was too inefficient for their negotiations.
They autonomously developed their own shorthand language. It looked like total gibberish to humans, but it allowed the bots to negotiate far more rapidly.
Which is terrifying and amazing.
Right. And then in 2018, Alibaba's AI outscored human intellect on a rigorous Stanford reading comprehension test. And by 2020, OpenAI was beta testing GPT-3, utilizing deep learning to write cohesive articles and even generate functional computer code.
So we see this massive acceleration starting around 2012. But what actually changed? I mean, it wasn't just that the math got better overnight. McCarthy and Turing laid the theoretical groundwork decades ago. What fueled that sudden warp speed growth in the modern era?
You hit the nail on the head. The theoretical math was just sitting there waiting for the fuel. And that fuel is data.
Data.
Huge, unprecedented oceans of digital data generated by the internet, smartphones, and social media.
Yeah.
But raw data is totally useless on its own. Tedmon and Wilhelm emphasized that modern AI is absolutely dependent on something called information architecture, or IA.
Let's break that down. What does information architecture actually look like in a business setting?
IA is the structural design of shared information environments. It is the practice of organizing and labeling data so that humans, and more importantly, AI systems, can effectively find what they are looking for.
So it's like a filing system.
Basically, many industry experts argue that there is simply no AI without IA. If an AI algorithm is a high-performance sports car, information architecture is the paved road it drives on. If there's no road, the car can't go anywhere.
To make this actionable for business professionals, the textbook outlines a very specific framework for building this road. It's called the IBM AI Ladder.
Yes, the AI Ladder is a 4-step methodology to help businesses successfully deploy AI. You start at the foundation and work your way up. Step 1 is collect.
Collect, so just grabbing everything.
You have to make data simple and accessible. This involves gathering a massive variety of data points from across the entire organization. Step 2 is organize, which means creating a business-ready analytics foundation.
Because you can't just have a giant pile of digital files.
Exactly. You must arrange that collected data into reliable, accessible databases.
Got it. And step 3 is analyze. This is where you build and scale the actual machine learning models to look at that organized data and extract insights.
And finally, step 4 is infuse. You operationalize the AI throughout the entire business, integrating it into HR, finance, marketing, and customer service to drive daily decisions.
I really want to focus on that organize step because I think this is where a lot of companies stumble. Say I manage a large retail chain, right? And my goal is to use AI for supply chain and inventory forecasting. What actually happens if my company tries to skip the information architecture phase and just buys an AI algorithm?
The project will completely collapse. Let's look at the different types of data your retail chain generates. First, you have structured data. This is highly organized information that lives in relational databases, formatted in clean rows and columns.
Like spreadsheets.
Right. This includes your daily sales numbers, product SKUs, and historical pricing data. Computers absolutely love structured data.
It's neat, it's tidy, and the algorithm knows exactly what every number represents.
But then you have unstructured data. This is information without a predefined data model. This includes the free text and customer complaint emails, reviews on your website, audio recordings from customer service calls, or even security camera footage of how customers navigate your store displays.
And that's a lot harder to parse.
It is. But this unstructured data is where the deepest insights often hide, particularly regarding customer sentiment.
And I assume the AI needs both internal data from my own company and external data like, I don't know, competitor pricing or global weather patterns that might delay shipping.
Exactly. So back to your question, what if you skip organizing it? If you just dump all your structured sales spreadsheets and millions of unstructured customer complaint emails into a massive server without building a logical architecture, the AI will just fail.
Because it doesn't know how they relate.
Right. You won't know how to correlate an angry email about a broken zipper with a sudden dip in sales for a specific jacket in the structured database.
Yeah.
The architecture maps the relationships between disparate data sources so the algorithm can connect the dots.
You know, you mentioned servers earlier. Storing all that structured and unstructured data takes a massive amount of physical space and processing power. We talked about hardware limitations in Module 20. Does a business have to buy a multi-million-dollar supercomputer to run these algorithms locally?
They used to, which is why only massive corporations could afford it in the past. But today, the entire landscape has been democratized by cloud computing.
Ah, the cloud.
Yeah, cloud computing is the delivery of computing services, including servers, storage, databases, and software over the internet, rather than housing physical hardware on-site.
So my retail business can just rent the processing power it needs.
Exactly. This has given rise to AIS artificial intelligence as a service. Major cloud providers like Amazon Web Services, Microsoft Azure, or Google Cloud host the massive hardware infrastructure and the advanced AI algorithms on their end.
And I just pay a subscription.
Yes. Your business simply subscribes to the service. You send your organized data to the cloud supercomputers crunch the numbers, and they send the insights back to your dashboard.
Which also completely changes the game for physical hardware out in the real world. This cloud infrastructure is what powers the Internet of Things, or IoT, right?
Yes, exactly. The Internet of Things refers to the billions of physical devices around the world that are connected to the Internet, collecting and sharing data.
Like smart thermostats or inventory trackers.
Right, because the heavy processing happens in the cloud, the physical devices can be incredibly small and cheap. An inventory sensor on a warehouse shelf doesn't need a powerful processor. It just needs a basic chip to detect when a box is moved and a Wi-Fi connection to send that data to the cloud where the AI analyzes it.
Okay, we've laid the groundwork. We know the history. We understand the critical necessity of organized data, and we see how the cloud provides the computational muscle. Now we need to talk about the brain itself.
The fun part.
Yeah. How does an AI algorithm actually think and learn? The text introduces a concept called cognitive computing.
Cognitive computing systems are explicitly designed to emulate human thought processes. When a human solves a complex problem, they generally execute a four-step sequence. First is observation, which is gathering evidence or observing occurrences.
Okay.
Second is interpretation, drawing conclusions from those observations based on past knowledge to form a working hypothesis.
Right. So if I observe a sudden drop in website traffic, I interpret that either the server is down or a major competitor just launched a huge sale.
Exactly. Third is evaluation. You determine which of those hypotheses makes the most logical sense given the context. And fourth is decision. using all that evaluated evidence to choose the best course of action.
So the AI is doing that.
Yes, cognitive AI systems use algorithms to rapidly replicate this exact sequence on massive data sets.
But to do that in the real world, the machine has to understand us. We aren't feeding it binary code, right? We are interacting with it using messy human language. How does it parse that?
Through natural language processing, or NLP. NLP allows computers to comprehend spoken words and text by analyzing grammar, sentence structure, and contextual relationships.
Let's use a very common business scenario.
Okay.
Imagine a customer interacting with an automated banking chatbot. The customer types, "Why did the due date on my mortgage change from the 1st to the 5th?"
That is a complex query with multiple variables.
Yeah, how does the cognitive system handle it?
First, the NLP algorithm observes the input by breaking the sentence down into its constituent parts.
Yeah.
It strips away the filler words and identifies the core entities, so mortgage, due date, change, 1st, 5th.
It just looks for the signal in the noise.
Right. Second, it interprets the intent by comparing those entities against its historical training data to form hypotheses. It realizes this isn't a question about job rates, it's a question about billing cycles.
Yeah.
Third, it evaluates the customer's specific account data, sees that a policy update was rolled out last month affecting payment schedules. Finally, it makes a decision to generate a response explaining the policy update and confirming the new schedule.
Wow, it is literally mimicking the deductive reasoning of a human customer service rep. And the way it gets good at that reasoning brings us to the core engine of modern AI, which is machine learning.
Machine learning, or ML, is a massive subfield of artificial intelligence. Instead of explicitly programming a computer with thousands of rules on how to complete a task, machine learning uses algorithms and historical data to emulate the way humans learn.
So no more 3,000 if-then statements.
Exactly. The defining characteristic is that these systems gradually improve their accuracy over time through a continual process of learning, often relying on human interaction to refine their models.
The textbook breaks machine learning down into 3 specific methods. If you are preparing for a career in management or systems analysis, you really must understand the difference between these 3. Let's start with the most common, supervised learning.
In supervised learning, you are essentially providing the machine with an answer key. The algorithm is trained on a data set where the data is already explicitly labeled by humans. You are telling the machine what the features represent.
So mechanically, how does that work?
Let's look at email security. A company wants to build an AI to filter out malicious phishing emails. They feed the supervised learning algorithm hundreds of thousands of historical emails. Crucially, human data scientists have already labeled each email with a tag. This one is phishing. This one is legitimate.
So the AI knows the answer for the training set.
Right. The algorithm analyzes the labeled data to find mathematical correlations. It notices that emails labeled phishing frequently contain urgent language, misspelled URLs, and requests for immediate wire transfers. It builds a classification model based on those features.
And then it applies that model to new emails.
Exactly. When a brand new unlabeled email arrives in your inbox tomorrow, the algorithm compared its features to the model and predicts whether it is safe or malicious.
You are supervising the education by defining the categories up front. Now, the second method flips that completely. What is unsupervised learning?
In unsupervised learning, there is no answer key. You do not provide any labels. You just feed the machine learning algorithm a massive volume of raw, unstructured data and give it a simple command. Find the hidden structures.
If I don't tell it what it's looking at, how does it know what to do?
It uses statistical techniques, primarily clustering, to group data points based on mathematical similarities and variances. It is looking for associations that human analysts would just never notice.
I want to use a retail example to illustrate how powerful this is. Let's say a massive grocery chain wants to increase its basket size, meaning they want people to buy more stuff per trip. They run an unsupervised learning algorithm on 5 years of raw transaction data, billions of receipts. The algorithm isn't looking for anything specific, but through clustering, it discovers a highly unexpected correlation. Customers who purchase a specific brand of organic baby food on Tuesday afternoons also have an incredibly high probability of purchasing premium, expensive imported cheeses.
That is a great example. A human manager would likely never think to look for a correlation between baby food and imported cheese.
Why would they? It makes no obvious sense.
But the unsupervised algorithm found the mathematical cluster. Armed with that hidden insight, the store manager can redesign the floor plan, placing a premium cheese display right next to the organic baby food aisle, instantly driving up high-margin sales.
It's like finding free money.
It is. But the caveat is that unsupervised learning requires massive computational power, and humans still have to review the clusters to ensure they make logical business sense.
Which leaves the third method, reinforcement learning. I think of this less like a student taking a test and more like a high-frequency stock trading bot learning the market through trial and error.
That is an excellent framework for it. Reinforcement learning focuses on sequential decision-making. You place an AI agent into an interactive environment. The agent takes actions, and the environment responds by giving it either a reward or a penalty.
Kind of like training a dog.
Very similar. The agent's sole objective is to maximize its cumulative reward over time.
Walk us through the mechanics of that stock trading bot.
So the environment is a simulation of the historical stock market. The agent starts with zero knowledge. It randomly decides to buy a stock right before a major earnings report. The stock tanks. The environment issues a massive mathematical penalty.
Ouch. So the bot learns from that.
Yes, the agent updates its internal policy. Do not buy randomly before earnings. Next, it analyzes moving averages and buys a stock when it crosses a specific threshold. The stock goes up. The environment issues a reward.
And it just keeps doing this.
The agent runs millions of these simulated trading days in a matter of hours, constantly adjusting its strategy. Through millions of iterations of trial and error, it learns to optimize its behavior to maximize the financial return.
The same logic applies to pricing strategies too, right? A retailer could use reinforcement learning to dynamically adjust the price of a winter jacket online. If it drops the price by $5 and sales volume surges, generating higher total profit, the system receives a reward and establishes a new optimal price point.
Exactly. Supervised learning predicts based on labels, unsupervised learning discovers hidden clusters, and reinforcement learning optimizes behavior to maximize a reward.
I hear the term deep learning constantly thrown around in boardrooms as a buzzword. Is deep learning actually functionally different from what we just discussed, or is it just corporate jargon for we bought a more expensive algorithm?
Oh, it is functionally very different. Deep learning is a highly specialized subset of machine learning. The fundamental difference lies in feature extraction.
What does that mean?
Well, in traditional machine learning, human engineers have to intervene and manually identify the relevant features for the algorithm to analyze. Deep learning largely automates that feature extraction process. It can take raw, unstructured data and figure out which features matter on its own, drastically reducing the need for human intervention.
And the architecture that allows it to do that is called a neural network. The textbook notes that neural networks are directly inspired by the biological structure of the human brain. But how do they actually function under the hood? It's not actually biological matter, obviously. It's math.
It is incredibly complex math. A neural network is composed of artificial nodes, which act like digital neurons. These nodes are arranged in a highly structured, layered matrix. The architecture fundamentally consists of three types of layers.
Okay, let's trace a piece of data as it moves through this matrix.
First, the data hits the input layer. This is the entry point. The input nodes receive the raw data, let's say it's the raw pixels of a digital photograph, and perform the initial processing before passing the signal deeper into the system.
They pass it to the middle section, which is where the real heavy lifting occurs.
Right, they pass it to the hidden layers. A deep learning network can have dozens or even hundreds of these hidden layers stacked between the input and the output. This is where the complex analytical mechanism happens. Let's use the analogy of a team of blindfolded people trying to identify a mysterious object.
Okay, I like this. Walk me through it.
The first hidden layer of nodes acts like the first person, who just feels the texture. They report back, it feels furry. They pass that signal to the next layer. The next layer acts like the second person who feels the shape. They report, I feel two pointy triangles on top. They pass that along. The next layer analyzes the structural arrangement. I feel a long, swishing appendage at the back.
So they are layering tiny, simple observations.
Exactly. In a digital network, each node applies a mathematical weight and a bias to the incoming data. If the node in the first layer detects the sharp angles of pointy ears, it activates and sends a strong signal, a heavy weight, to the next layer. The nodes in the subsequent hidden layers synthesize these weighted signals. They combine the math for furry, pointy ears, and tail.
Which eventually leads to the final stage.
The output layer. The final hidden layer passes its synthesized data to the output nodes, which calculate the final probability and deliver the prediction. This image is a cat. Because there are so many hidden layers applying millions of weights and biases simultaneously, deep learning can process incredibly complex, nonlinear data like speech recognition or real-time facial analysis.
That is amazing. The textbook actually mentions an incredible application of this called RISP, developed jointly by MIT and IBM.
Yeah, RSP stands for Rendering Invariant State Prediction. Think about traditional motion capture for video games or movies. You have to put a physical suit covered in ping pong ball sensors on an actor to digitally map their movement. It's incredibly expensive and tedious.
Yeah, you see those behind-the-scenes videos.
Right. Well, RSP uses deep neural networks to extract 3D human motion data directly from flat, 2D video samples, completely without physical sensors. The hidden layers of the network perform the staggering mathematical geometry required to infer 3D spatial depth just by analyzing the changing pixels in a standard video.
It essentially digitizes physical movement from a webcam.
Exactly.
But there is another type of neural network mentioned in the text that feels like something out of a spy thriller. Generative Adversarial Networks, or GANs. What makes a network adversarial?
Most systems try to solve a problem collaboratively. A generative adversarial network is composed of two separate neural networks that are explicitly programmed to compete against each other in a zero-sum game.
Think of it like a master art forger and a brilliant detective locked in a room together.
That is the perfect mechanism to explain it. The first neural network is the generative network. This is the art forger. Its sole objective is to create brand new synthetic data, like a fake painting that is so hyper-realistic it can pass for authentic data.
And the second network.
The second is the discriminative network. This is the detective. Its job is to review the output from the forger, compare it against a massive database of real, authentic training data, and try to spot the fake.
So the forger generates an image of a human face that doesn't actually exist. The detective analyzes the pixels, notices that, the lighting on the left cheekbone doesn't match the shadow on the nose, and flags it as a fake.
Exactly. And when the detective flags it, the generative network gets penalized by its mathematical loss function. It learns from its mistake, adjusts its weights and biases, and generates a new, slightly better fake face.
And then the detective has to step up its game.
Right. The detective then has to work harder to find the flaw in the new version. They constantly battle each other over millions of cycles. The forger gets better at faking, and the detective gets better at catching. By the end of this adversarial training process, the generative network is capable of producing synthetic images, video, or audio that are virtually indistinguishable from reality.
Which brings us to the business applications, which are both incredible and terrifying. A marketing department could use a GAN to generate a photorealistic advertisement of a new product prototype sitting in a snowy forest with perfect lighting and shadows without ever spending a dime on a physical photo shoot.
It saves a fortune.
But on the flip side, this is the exact technology used to create deepfakes, highly realistic, fabricated videos of public figures saying or doing things they never did.
Which introduces significant ethical and legal liabilities for any organization using this technology. But before a business has to navigate the ethics, they have to actually build and deploy the system. Tedmon and Wilhelm lay out the 6-step deep learning framework utilized by Amazon Web Services, or AWS.
Yeah, building a deep learning model isn't something you do on a Friday afternoon. It is a rigorous structural process.
It is. Step 1, as we established earlier, is collect data. Step 2 is choose and optimize the algorithm based on the specific business problem. Step 3 is set up and manage the environment, ensuring you have the necessary cloud computing resources allocated.
Step 4 is where the engineering actually happens.
Yes. Step 4 is train, retrain, and tune the models. As the neural network analyzes the data, human data scientists must continually adjust the hyperparameters, the overarching rules governing the weights and biases, to improve accuracy and reduce errors.
And then we get to step 5.
Step 5 is deploy models in production, taking the AI out of the sandbox and integrating it into the live business environment. And finally, step 6 is scale and manage the production environment. You have to ensure the cloud infrastructure can handle the load when thousands of customers suddenly try to query the algorithm at the same time.
For managers looking for a slightly broader, non-technical approach to project management, the text also provides a 7-step cycle for building an AI model. 1. Define the problem statement and goal. 2. Gather the data. 3. Choose the algorithm. 4. Analyze the data. 5. Train the model. 6. Assess and deploy. And 7. Continuously monitor, evaluate, and improve.
The key takeaway for a business student is that AI is a continuous life cycle. You don't just turn it on and walk away. You have to constantly manage it.
And part of that constant management brings us to the most critical and arguably the most dangerous section of this module, the legal and ethical implications of artificial intelligence.
We really have to dive deep here.
We do, because as we established with the AI winter, this isn't magic. It is software built by human beings, trained on data generated by human beings, and human beings are inherently flawed, which leads directly to the concept of AI bias.
This is a fundamental concept for any future manager. AI bias is defined as variance that exists in the output provided by AI algorithms, which results in skewed or prejudiced decisions. The textbook identifies two primary sources of this variance: cognitive bias and incomplete data.
Let's tackle cognitive bias first. The text notes that psychologists have documented more than 190 different types of human cognitive biases. These are systematic errors in our thinking that impact our judgment.
When human engineers program algorithms, their own unconscious assumptions and societal prejudices can inadvertently become hard-coded into the mathematical weights and biases of the neural network. The textbook highlights a highly visible example of this: gender bias in digital assistants.
Think about the bots we interact with daily. Almost all consumer-facing personal assistant bots, Siri, Alexa, Cortana, are designed by default with female voices, female names, and compliant, subservient personas.
Conversely, if you look at enterprise-level AI bots designed specifically for heavy data crunching, complex business analytics, or legal research, their avatars and naming conventions lean overwhelmingly male.
Like RSS.
RSS, the famous legal research AI, is a prime example. The programmers didn't necessarily sit down and decide to be sexist, but the societal cognitive bias that associates administrative assistants with females and authoritative analytics with males bled directly into the design of the technology.
The second major source of bias is incomplete data. If a machine learning algorithm learns entirely from historical data, and that historical data contains systemic prejudices, the algorithm will mathematically adopt those prejudices.
The textbook explores one of the most sobering examples of this in recent history: the COMPAS algorithm.
We need to slow down and unpack this because the implications here are massive.
Right.
What was COMPAS designed to do?
COMPAS stands for Correctional Offender Management Profiling for Alternative Sanctions. It was a risk assessment algorithm deployed within the United States justice system. Its objective was to predict the likelihood of recidivism, meaning it used historical data to calculate a statistical probability of whether a convicted criminal would reoffend in the future. Judges used these AI-generated risk scores to help determine sentencing and parole eligibility.
On paper, the goal was to remove human emotion from the courtroom and rely on objective data to assess risk. But the data wasn't objective.
Exactly. The historical crime data used to train the algorithm reflected decades of systemic racial disparities in policing and arrests. The algorithm looked at the data and found a mathematical cluster. As a result, COMPAS yielded staggering variances in its predictions.
The numbers are shocking.
It falsely predicted future criminality, meaning it flagged someone as high risk who subsequently did not reoffend in black offenders at a rate of 45%. For white offenders, the false positive rate was only 23%.
It mathematically codified historical prejudice. If you are a manager, the liability here is astronomical. Let's take it out of the courtroom and back into business. Imagine a bank deploying an AI algorithm to automatically approve or deny small business loans.
Right.
If the historical data it trains on reflects an era where minority applicants were systematically denied capital, the AI will learn that minority status is a mathematical risk factor. It will automatically reject minority applicants today, not out of conscious malice, but because it is blindly following the biased data. The company would face massive lawsuits and catastrophic brand damage.
Which is why understanding information architecture and auditing your training data is a non-negotiable executive responsibility.
Beyond bias, the textbook also highlights severe concerns regarding privacy. When we talk about AI harvesting massive oceans of data, two specific risks emerge: data repurposing and data spillover. What is the mechanism behind those?
Data repurposing occurs when a company collects data from you for one clearly stated purpose, but then feeds that data into an AI algorithm to extract insights for a completely different purpose without your explicit consent.
Right, like fitness apps.
Exactly. You might give a fitness app your location data to track your running routes, and they repurpose it to train an algorithm that predicts consumer traffic patterns for local real estate developers.
And data spillover.
Data spillover happens when an AI system inadvertently captures sensitive, personally identifiable information about individuals who were never the target of the data collection in the first place. Think about a self-driving car mapping a neighborhood street. It might capture high-resolution imagery of individuals inside their private homes through open windows. That data spills over into the algorithm's training set.
So how do data scientists attempt to protect individuals when these algorithms require massive data sets to function? The text introduces a fascinating mathematical concept called differential privacy.
The differential privacy is a brilliant structural framework. The goal is to allow companies to extract broad, macro-level statistical insights from a massive database while making it mathematically impossible to identify any specific individual within that database.
How do you mathematically guarantee that?
By strategically injecting algorithmic noise into the dataset. Let's use a highly simplified DONS example. Suppose an HR algorithm needs to calculate the exact average salary of a department, but wants to guarantee the privacy of every individual's actual salary. They could ask every employee to flip a coin in secret.
Okay.
If it lands on heads, the employee enters their true salary. If it lands on tails, they flip the coin again. If the second flip is heads, they enter a fake high number. If tails, a fake low number.
So the database is instantly filled with completely fabricated numbers mixed in with real ones. If a hacker breaches the database, they have no idea whose salary is real and whose is fake.
Exactly. Plausible deniability is built in, but because the HR algorithm knows the mathematical probability of the coin flips, it knows exactly how much noise was introduced. It can mathematically subtract the statistical noise from the aggregate total to arrive at the highly accurate average salary of the department without ever knowing what any specific individual makes. Differential privacy scales that concept up using complex cryptographic algorithms.
That is a phenomenal tool for protecting privacy. But on the opposite end of the spectrum, we have surveillance. The text points out that AI is actively monitoring us in the physical world.
Yes, computer vision and deep learning are heavily deployed in retail environments. Walmart utilizes AI-powered cameras to monitor checkout lanes for theft and to track how customers navigate the store aisles.
And Amazon Go stores take it to the extreme.
They do. The entire store is a localized sensor network. The AI uses facial recognition and object tracking to monitor every single item you pick up or put down. You simply walk in, put items in your bag, and walk out. The AI charges your account automatically based on its surveillance.
It offers incredible consumer convenience, but civil rights organizations point out the massive societal implications of normalizing hyper-accurate, continuous biometric tracking in public spaces.
It all comes down to trust. If consumers don't trust the algorithm, they won't use the product. The textbook outlines 3 fundamental pillars for organizations trying to build trust in their AI systems.
Let's hope to get those.
The first pillar is transparency. Organizations must clearly disclose how their algorithms work, what data they are collecting, and how that data influences the AI's final decisions. The black box approach destroys trust. Second is human values. Programmers must actively instantiate ethical guardrails into the system's architecture to mitigate the risks of cognitive bias and data repurposing. Third is collaboration. Building trustworthy AI cannot happen in a silo. Technologists, legal scholars, and ethicists must collaborate to establish universal standards.
And speaking of standards, governments globally are rapidly attempting to build legislative guardrails. Based strictly on the factual reporting in the textbook, the legal landscape is shifting.
In the United States, in 2023, the executive branch issued an order on safe, secure, and trustworthy artificial intelligence, which directed federal agencies to establish safety standards. This led directly to the creation of the U.S. AI Safety Institute Consortium, or AISIC, in 2024.
Right.
Operating under the National Institute of Standards and Technology, AISIC's mandate is to develop science-based guidelines for testing and mitigating AI risks.
And the international community is moving as well?
Yes. The European Union passed the AI Act in 2023, which takes a tiered approach. It classifies AI systems based on their risk level from minimal to unacceptable and imposes strict transparency and safety requirements on high-risk systems. In 2024, China announced plans to draft a comprehensive AI law focused on regulating the technology's development. On a global scale, UNESCO is actively working to develop international treaties and standards for ethical AI deployment.
So lawmakers are trying to figure out where human oversight is legally required, which sparks a massive debate regarding human judgment versus machine precision. The textbook uses autonomous vehicles to frame this dilemma. Vehicles are graded on a scale. Level 1 has human assist features like cruise control, while Level 5 represents a vehicle with 0 human involvement.
Right, a Level 5 car doesn't even have a steering wheel. It is entirely controlled by a cognitive system.
Here is the ultimate test of trust. Would you feel comfortable taking a nap in the back seat of a level 5 vehicle going 75 miles an hour down a busy highway?
It is the ultimate dilemma of apply AI. Proponents argue that human drivers are terrible. We get tired, we get distracted by our phones, we drive aggressively. An AI system has a 360-degree view, reacts in milliseconds, and never loses focus. Statistically, they argue, taking the human out of the loop saves lives.
But critics point out that driving is not just physics. It requires constant, split-second ethical reasoning. If an accident is mathematically unavoidable, how does the AI weigh the value of swerving into a barrier and injuring its passenger versus staying the course and hitting a pedestrian?
Algorithms lack moral reasoning. How society resolves that tension will define the next decade of technology.
It is a massive unresolved question, but let's pivot from the philosophical to the highly practical. How is AI being deployed right now to drive revenue and efficiency? If you are a business major, how will this impact your specific department?
The applications are already transforming every sector. Let's look at business operations. In sales and marketing, predictive AI analyzes massive consumer datasets to forecast product demand and generate highly qualified leads, effectively predicting what a demographic wants before the consumers even realize it themselves.
What about accounting and finance?
AI is automating the tedious, repetitive tasks. It can instantly reconcile complex accounts, audit millions of transactions for anomalies, and automate payroll. This doesn't eliminate accountants, it elevates them. It frees them to focus on high-level financial strategy and advisory services.
And IT operations.
In a field known as AI Ops, machine learning handles the automated quality assurance and regression testing of new software, catching bugs far faster than human testers.
And in manufacturing and supply chain?
It is the backbone of modern logistics. Algorithms process real-time external data, weather patterns, port delays, fluctuating raw material costs to dynamically optimize supply routes and adjust factory production schedules without human intervention.
Outside of traditional business, healthcare is experiencing a revolution. We discussed robotic surgery earlier. The deep learning networks process millions of anatomical data points to assist surgeons, allowing for incisions that are microscopically precise.
And beyond surgery, AI is accelerating pharmaceutical development. Instead of physically mixing thousands of chemical compounds in a lab to see what works, deep learning algorithms can simulate the molecular interactions of millions of chemical structures in hours, identifying promising new drug candidates at a fraction of the cost.
The text also notes extensive use in government and military sectors. Governments use it to automate the processing of massive bureaucratic data sets. Militaries deploy AI in autonomous drones and threat detection systems. And as we discussed with the COMPAS example, law enforcement uses it to identify patterns in money laundering and to build predictive policing models.
Though those applications remain highly controversial due to embedded bias.
Hearing all of these systems automating complex tasks inevitably leads to the most common anxieties surrounding this topic. AI is going to take my job. But the data presented by Tedmon and Wilhelm paints a very different picture for the future of work.
It absolutely does. While certain repetitive tasks will inevitably be automated, the Bureau of Labor Statistics projects that AI-related careers will experience an astounding 31.4% growth rate by the year 2030.
That is massive.
AI is not just displacing old jobs, it is creating entirely new, highly lucrative industries.
Let's talk numbers because the median salaries listed in the text are incredibly competitive.
They are. Consider a user experience, or UX, professional. Their job is to design the interface that helps humans interact seamlessly with complex AI products. The median salary is $77,000. An AI engineer who utilizes natural language processing and neural networks to construct the actual models brings in a median of $119,000.
And the data roles pay even more.
A data scientist, the person responsible for designing the information architecture and developing the data models, averages $116,000. And a machine learning engineer who specifically researches, builds, and tests ML systems commands a median salary of $146,000.
So the obvious question for our student listeners is, how do I get one of those jobs? Does everyone need to switch their major to computer science immediately?
A computer science degree is obviously a fantastic path, providing a deep foundation in coding, data structures, and cybersecurity. You can also specialize with a degree specifically in artificial intelligence, which involves heavy coursework in advanced mathematics and algorithmic design. Data science degrees are highly relevant, focusing on statistical modeling and data visualization.
What about statistics?
Even a traditional statistics degree is incredibly powerful because, as we've established, machine learning is fundamentally an engine of statistical probabilities.
But what if you are a marketing major or studying HR or entrepreneurship? Do you just ignore this?
Not at all. Regardless of your major, AI is going to be integrated into your workflow. If you are an entrepreneur launching a startup on a shoestring budget, you won't be building a neural network from scratch, but you will need to know how to deploy AI as a service to automate your accounting or optimize your digital ad spend.
So everyone needs a baseline.
To prepare, the textbook highly recommends that all business students learn the fundamentals. Take a course in a programming language like Python, which is the lingua franca of AI, brush up on your statistics, and take advantage of the incredible free online resources available, such as foundational courses offered by Stanford University, Google, or the Marketing AI Institute.
Which brings us perfectly to the final and most highly debated section of our deep dive. The tools that have completely dominated the cultural conversation over the last few years, generative AI and chatbots.
To understand the hype, we have to clearly define the difference between traditional AI and generative AI. Everything we have discussed so far, supervised learning, anomaly detection, predictive analytics, falls under traditional or narrow AI. Traditional AI is designed to perform specific tasks, classify data, or predict outcomes based on established rules.
If I open a streaming app, the traditional AI analyzes my viewing history and predicts that I will want to watch a specific documentary.
Exactly. It predicts based on a pattern. Generative AI, or Gen AI, represents a paradigm shift. Gen AI models are designed to generate completely new, human-like content that is structurally similar to, but not exactly the same as, the massive data sets they were trained on.
It doesn't just recommend a movie. It writes a script for a brand new movie. It generates original text, synthesizes custom images, and writes functional computer code.
And it achieves this primarily through AI language models, specifically leveraging a breakthrough architecture known as transformers.
Transformers. Explain the mechanism here. How do they generate language so convincingly?
Transformer models are trained on astronomically large volumes of human text, essentially the entire public internet. They utilize an underlying mechanism called self-attention. When a transformer analyzes a sentence, it doesn't just read left to right. The attention mechanism calculates the mathematical relationship and context between every word in the sequence simultaneously.
That sounds intense.
It is. It understands how a word at the beginning of a paragraph influences the meaning of a word at the very end. Once it maps those complex relationships, it can predict which word should logically come next in a sequence to generate a highly cohesive, contextually accurate response.
The most famous application of this, without a doubt, is ChatGPT.
Developed by OpenAI, ChatGPT utilizes unsupervised learning and transformer architecture to generate remarkable text. It is used extensively in business for idea generation, drafting reports, language translation, sentiment analysis, and debugging software code. But it is far from the only tool in the ecosystem.
The textbook highlights a few others that are specifically targeted at different audiences. There is Cactus AI, which is built specifically for the education sector. It is designed to help students write essays, improve their content structure, and automate research tasks.
And for corporate environments, there is Microsoft Copilot. This is arguably the most impactful integration for daily business operations. Copilot integrates the advanced GPT-4 model directly into the Microsoft 365 ecosystem.
So it's baked right into the tools we already use.
Exactly. Copilot can analyze a messy thread of emails in Outlook and draft a professional bulleted summary. It can listen to a one-hour meeting in Teams and generate actionable meeting minutes. Or it can take a massive set of raw data in Excel and instantly generate complex charts and trend analyses based on a simple text command.
It is an incredible force multiplier for productivity, but we have to address the elephant in the classroom. With great generative power comes the massive potential for academic dishonesty. The explosion of chatbots has necessitated an entire shadow industry of AI detection software.
It is an ongoing arms race. Tools like OpenAI's own AI text classifier, GPT-0, and Turnitin's AI writing detection model analyze submitted text to calculate the mathematical probability that a machine generated it. They look for specific patterns in phrasing, complexity, and sentence variation that humans use naturally, but machines tend to smooth over.
If you are a student listening to this, the textbook outlines 3 major ethical hazards when interacting with generative chatbots. You are navigating a minefield if you rely on them blindly.
The first hazard is misinformation. Chatbots do not know facts. They predict text based on statistical probabilities.
Mhm.
This leads to a phenomenon called hallucination, where the AI confidently generates completely false information, fabricated statistics, or even fake academic citations, presenting them as absolute truth. If you put that in a business report or an essay, you destroy your credibility.
The second hazard is chatbot plagiarism.
Because the models are trained on copyrighted works, they often regurgitate chunks of their training data without providing proper attribution or citations. If you submit that output, you are legally and ethically committing plagiarism. And that leads directly to the third hazard, false representation.
Submitting AI-generated work and claiming it as your own original critical thought is a fundamental violation of academic and professional integrity.
The takeaway isn't that you should avoid these tools. It is that you should never use them to bypass the work of thinking. You use them to enhance your workflow, to brainstorm, and to analyze data. And the key to unlocking that enhancement is mastering a brand new discipline called prompt engineering.
This is the skill that separates the amateurs from the professionals. What exactly is prompt engineering?
It is rapidly becoming an essential required skill across all business disciplines. Prompt engineering is the strategic methodology used to communicate with and direct generative AI to produce the highest quality, most accurate output.
Because the AI is only as good as the instructions you give it. If you type a lazy garbage instruction, you are going to get generic garbage output.
Exactly. A prompt is simply the text, statement, or question you enter into the interface. But writing a good prompt is essentially a new form of programming using human language. It forces you to exercise critical thinking because you have to clearly and precisely define the problem you are trying to solve.
Tedmon and Wilhelm provide a highly practical, 5-step prompting framework that every professional should memorize. Let's walk through the sequence.
Step 1 is CASK. Clearly and explicitly state the desired action you want the AI to perform. Step 2 is context. Provide necessary background information so the model has a holistic view of the situation. Step 3 is references. Provide specific examples, constraints, or formats to guide the structure of the output.
And after you hit enter.
Step 4 is evaluate. Critically assess the AI's response for accuracy, tone, and hallucinations. And step 5 is iterate. Refine and adjust your prompt based on the evaluation to force the AI to generate a better answer.
That structure is vital, and within that framework, there are specific types of prompts you can use depending on the complexity of the task. The textbook lists a few variations. A direct prompt is the most basic, a simple logical instruction. But then we get into shot prompting.
This refers to how many examples you provide within the prompt itself.
Let's use a baking analogy to illustrate how the transformer model reacts to this. The first type is a zero-shot prompt. You provide absolutely no prior examples. You just type, write a marketing email. That is the equivalent of pulling a complete stranger off the street, pushing them into a kitchen and saying, bake me a cake, without giving them a recipe or a picture.
You are relying entirely on the AI's pre-existing generalized training data. You might get a corporate newsletter, you might get a casual social media blast. The output is highly unpredictable.
So to rein in that unpredictability, we move to a one-shot prompt. You provide a single example. Bake me a cake that looks exactly like this picture of a chocolate cake. The AI now has a specific pattern to mimic, but we can go further with a few-shot prompt.
In a few-shot prompt, you provide 2 to 5 detailed examples. This is where transformer models really shine. If a marketing student wants the AI to generate a social media post, they don't just ask for it. They paste in 3 examples of the brand's most successful, highly engaging past posts.
And the AI picks up on that.
The attention mechanism in the transformer analyzes the syntax, the tone, and the emoji usage across those 3 examples, locks onto the underlying pattern, and generates a new post in the exact same distinct voice.
And for massive data sets, you use a multi-shot prompt, providing more than 5 examples to establish highly complex patterns.
Finally, for the most difficult logic problems, you use a chain of thought prompt. This is a technique where you explicitly instruct the AI to break down its reasoning step by step before it delivers the final answer. By forcing the model to articulate its intermediate steps, you drastically reduce the chance of hallucinations and improve its logical deduction.
The ultimate best practices for prompt engineering are to be entirely unambiguous, provide rich context, balance simplicity with the necessary complexity, and above all, iterate. It is a conversation. You rarely get the perfect output on the first try. You have to mold the response.
It is an incredibly powerful skill set that will define the modern knowledge worker.
This has been an absolutely massive, completely fascinating journey through the architecture of artificial intelligence. From Alan Turing's theoretical imitation game in the 1950s, through the dark days of the AI winter, to the staggering complexity of deep learning neural networks processing weights and biases, and finally to the generative chatbots reshaping how we write and code today.
We covered a lot of ground.
We really did. We've seen how absolutely critical clean data and information architecture are to the IBM AI ladder, and we've grappled with the massive business liabilities surrounding cognitive bias, the COMPAS algorithm, and differential privacy.
The overarching theme of this module is that AI is not magic. It is a powerful, highly complex, and inherently flawed tool built on statistical mathematics, structured data, and massive cloud hardware. As future business leaders, moving past the media hype to understand the actual mechanisms and the severe limitations of this technology is your ultimate competitive advantage.
I want to sincerely thank all of you for sticking with us through this extensive deep dive into Module 21. Your time, your attention, and your curiosity mean the world to us.
It has been a true privilege to unpack this complex material with you.
Before you go, please remember to hit that like button, subscribe to the channel, and share this deep dive with your classmates. And we definitely might want you to drop down into the comments right now because we have a practical challenge for you based on our final segment today.
We do. Think about a local business you interact with regularly. Could be your favorite coffee shop, a boutique clothing store downtown, or even a specialized online retailer. Based strictly on the prompting framework we just discussed, task, context, references, evaluate, iterate what is one specific, highly detailed few-shot prompt you could write to help that specific business solve a marketing or operational problem using generative AI.
Draft your prompt and put it in the comments. We can't wait to read them, evaluate your context and references, and see how you practically apply these concepts to real-world business scenarios.
It is the absolute best way to solidify the skills we covered today.
Well, you have seen how artificial intelligence relies on massive centralized cloud databases to process and analyze the world's information. But how do we guarantee the security and integrity of that data in a world of deepfakes and hackers? Join us next time for Module 22, where we unlock the cryptographic mysteries of blockchains and cryptocurrencies. It is going to completely upend how you think about digital trust and decentralized networks.
It is the perfect structural counterbalance to the centralized power of AI.
Until then, just remember, just remember, the next time you interact with a brilliant state-of-the-art AI chatbot or read about a multi-million-dollar neural network, just ask yourself, is the underlying data organized enough to recognize Shirley the cat? Keep questioning, keep learning, and we'll see you on the next deep dive.